let's start today with a little bit of a review of our MR basic principles and really talk about how that net magnetic vector gets flipped into the transverse plane, because what we're going to talk about today is what happens when we turn off that RF pulse and then we allow those tissues to relax. So we're going to hear this term relaxation a lot in this unit. And relaxation really gives us our image contrast. So that's what we're going to be talking about this unit, image contrast. And then the other thing is image weighting. And that's how us as technologists can manipulate the parameters to get the desired image contrast that we want. And you can see here we have various image weightings down here, and we'll talk about some of these and how to recognize these different images as you start to get in the clinic, because that will be necessary not only for the registry, but as you're working in your clinical rotations, you should be able to quickly identify a T1 versus a T2 or a proton density weighted image. So we're going to get to that today. So let's do a little bit of review. So I'm not going to go over everything, but let's draw our coordinate system, and I'm just going to draw two axes. So we have our, what axis is this running straight up and down?
Longitudinal.
Longitudinal, okay, and that's denoted by M sub 0. M sub 0 or M sub Z. Yeah. So you can have two different labels for it. Okay? And then here we have the what plane?
Transverse.
Transverse plane, that's denoted by
MXY.
MXY. And we're just going to draw it two-dimensionally for right now. All right. And then we have our first magnetic field, which was B sub 0, which was static. It's not moving. And so our net magnetic vector aligned with B sub 0 along the longitudinal axis. So I want to draw that vector in a different color here. Okay. And we know we created this net magnetic vector by having an excess of spin-ups, which were our low energy hydrogen protons. And then when we applied an external radio frequency pulse, which was denoted with what? Not B0, but B sub 1. So this was our second magnetic field. And is this one moving or is it stationary?
Oscillating.
It's oscillating, so it's moving, right? And what frequency is it oscillating at?
The same as the active nuclei.
Same as the active nuclei. And at 1 Tesla, that was 42.57 megahertz. Okay? But it changes based on the static magnetic field. So that's where that Barmar equation comes into play. All right. So then we got to flipping this net magnetic vector into our transverse plane. And that flip angle was based on two things. What were those two things that determine a flip angle?
Amplitude and duration.
Amplitude and duration. Good. So in the simplest form, we just talked about how our flip angle thus far is 90 degrees. Because that's desired because this is where our coil lays on the patient, right? And this vector is going to flip into the transverse plane. And if we think about it three-dimensionally, it's going to oscillate or rotate around this transverse plane. A rotating magnetic field that comes across a stationary coil will induce a voltage in that coil. So we'll get some kind of potential difference. A voltage will be applied, and then that will ultimately be carried to our computer system, right? I'm going to draw a little computer over here. All right. And ultimately we get our image. But we have to do one more thing, and we have to do it a lot of times because these pulse sequences require repetitive excitation pulses and then letting the tissues relax and then constantly doing that over and over and over and over again. So now let's think about having that vector in the transverse plane. Okay, so I'm going to draw my two axes again. Now we have that vector in the transverse plane, which is desired for signal reasons. Okay? But we have vectors for all different tissues. Okay? We don't have really just one vector. We have vectors for CSF. We have vectors for gray matter, white matter, all the tissues in our body. Okay? And if all those vectors, and I'm just going to draw like a couple, let's give orange, that's another vector. And each color represents a different tissue. So think of it that way. Okay? So at this point, all those vectors are in that transverse plane, and you have that entire vector of that tissue. Do you think at this point we get any kind of contrast with those tissues? No, because they're all at 100%, right? We need to see different shades of gray and different signal strengths, right? So what we do is we turn off this RF pulse, and these vectors slowly decay, or quickly decay actually, and then they recover along this longitudinal plane, okay? Because remember, this is where they're ultimately the happiest, where they return to its lowest energy state. Okay? But what's cool about all these different tissues, based on just kind of their molecular structure, is they relax or decay and recover at different times. And they're all usually in the range of milliseconds, but they decay and recover at different times. Okay? So now I'm just going to kind of show you as they recover at different rates. Now all these vectors have different lengths to them, right? So when we have vectors with different lengths, and remember our vectors are ultimately our signal, we're going to get contrast on our image, okay? So that's really what we're talking about, and that's how our previous unit led up to today. Does anybody have any questions about that? All right. So we're going to discuss image weighting and contrast. So you see down here some different MR images. We have a T2, a T1, a STIR, which is short for a short tau inversion recovery, a T2 star, and the star is a little bit different from just a normal T2 because this is acquired with a gradient echo pulse sequence, a flare, which is a fluid attenuating inversion recovery, which is great for detecting MS lesions, a T1 post-gadolinium, because we know gadolinium really helps increase our contrast in tissues so that we can see cancers and other pathologies a little bit better. And then a diffusion-weighted imaging, which is great for visualizing acute strokes. So MRI, we're really imaging the same part and sometimes getting axial slices of that same area. But then what we do is we manipulate the parameters, image weighting, to get a different type of contrast. And each image is really important for sometimes just one or two things. Flare, I'm trying to rule out MS, and I'm also really highlighting other pathologies. Diffusion, great for strokes and detecting other pathologies that have restricted diffusion. So it's like the radiologist kind of goes through each sequence and goes, okay, you know, I see it something on the flare, but then, and then I compare it to the diffusion. Okay, that makes me, it's definitive now, it's an acute stroke. So you're getting all this information. It's kind of like solving a crime with all these different clues, with all these different types of image weighting images that you get in MRI. So if you ever had any question, like why are they getting multiple acquisitions of an axial, and this is the reason why. We don't just get one axial, one coronal, one sagittal, and call it a day. All right, so the objectives for this unit, we're going to talk about our parameters, but there are two different types. We have intrinsic and extrinsic, and we'll go over the difference. We're going to review contrast mechanisms, relaxation in different tissues, and the two main tissues we really like to talk about, and the book talks about a lot, is fat and water. Because just how they're made up, they're completely different molecules. One's very big, fat, and one's very small, water. And how they interact with other tissues is very different. So the literature commonly refers to, in this unit, fat and water because they're on the opposite end of the spectrums. We're going to talk about T1, T2, and proton density contrast and how you obtain that contrast through image weighting, partial saturation, and then we're just going to identify images. So for one of the quizzes in this unit, you're just going to get images, and you're going to have to determine if it's a T1, T2, or proton density. Because we're going to slowly work up to like flares and stirs and stuff like that. All right. So, as I was saying, different amounts of signal creates our contrast. The computer can only read out a signal that is in the transverse plane. So if you have a large vector in the transverse plane, like we have with this white vector, you're going to get high signal. And I gave it the color white because if you have high signal, that's going to appear bright on the image. Okay? If you have very low signal, we have a small vector denoting low signal in the transverse plane. You're going to get black on your image. And then if you have intermediate signal or a vector that has a medium length, you're going to get gray on your MR image. Okay? But remember, we're going to have all different vector sizes depending on the tissue that we're imaging. So let's talk about the difference between contrast and weighting. So the difference in how fat and water vectors recover and decay creates image contrast. And we know that that goes along with all tissues, but remember, I'm going to start talking about fat and water the most. And image contrast, it's no different from our X-ray definition of image contrast. It's really just the difference between black and white, or you could even say grays on the image. Shades of grays. But image weighting is how we manipulate the sequence parameters, determines image weighting. So over here we have an axial slice of the brain that's T2 weighted. And I know that because water, or CSF, in these ventricles, the lateral ventricles, is bright. Water, or CSF, due to its properties, takes longer to decay. So we manipulate our T2 parameters to highlight water, usually. And T2 weighted sequences are great for pathology because usually pathology has some component of water in it. All right, so let's talk about those two types of parameters. In MRI, you have either intrinsic or extrinsic contrast parameters. And this was always a registry question, so I'm going to hit on these a lot for my test. So make sure you really highlight this slide. So intrinsic contrast parameters, these are things that cannot be changed by us, the MR technologists, because they are inherent to the body's tissue. So tissues recover at specific times. We can't change that, depending on the field strength. Tissues also decay at specific times. We can't change that. Certain tissues have what we call higher proton or spin density than other tissues, so we'll get to it, but tissues like muscle and bone, they have a higher rate of hydrogen protons within those tissues compared to like lungs. Lungs tissue is just really air, so there's really not many hydrogen protons within your lungs. So MRI is really honestly not that great at imaging the lungs, so other modalities are usually better for like, detecting any pathologies within the lung, or and things like pulmonary embolism. That MRI is not usually the first modality of choice there. It's usually CT. And the reason is because lung is just air, and there's really no hydrogen spins within air. Flow, and right here they're talking about vascular flow or CSF flow. And then apparent diffusion coefficient, and that's just talking about how water diffuses across cell membranes. So we can't change that. That's inherent to the body. But things that we can change are called extrinsic contrast parameters. So as an MRI technologist, we have the luxury in our parameters card to manipulate these things to get that desired weighting. So the first one, and make sure to write these down, TR, that's repetition time. TE, echo time. Flip angle, you guys already know what that is. TI, that's inversion time. Turbo factor, which is also referred to sometimes as echo train length. That's what ETL stands for, echo train length. And then B value. And this is in relation to diffusion. The B value, it's Brownian motion. That's what the B stands for. And it's really just the rate of diffusion. So let's compare that to X-ray. What do you think an intrinsic characteristic contrast parameter is in X-ray? Something that we can't change.
Tissue density?
Tissue density, thickness, right? We can't change the body habitus of our patient. Good. What would be an extrinsic contrast parameter in X-ray?
Technical factors?
Technical factors, so give me a couple.
If you know that the patient has like a prosthetic, you would change it. You wouldn't use AEC on that one.
Good, good. So setting our techniques manually, so KVP and MAS, focal spot size, AEC, the cells that we're selecting. So all those things we can select on our console would be considered extrinsic parameters in X-ray. All right, so let's talk about our contrast mechanisms. We have three. So images in MRI obtain contrast through T1 recovery, also referred to spin lattice. So make that relationship. Spin lattice is T1 recovery. The second way we obtain contrast is through T2 decay, which is also referred to as spin-spin. And when we talk about spin lattice, it's really discussing how the spin, and the spin we're referring to is our hydrogen proton, is giving off energy to the lattice, which could be the neighboring, or I'm sorry, the surrounding environment. So lattice thinks surrounding environment, giving energy off to the surrounding environment. And remember, we gave energy into these spins by applying that RF pulse. Remember that? We went from low to high energy by applying that external RF pulse, B1. Now we're talking about how these tissues relax. Spin, spin, we're giving off energy to its neighboring spin. So when we're talking about these two things, T1 and T2 relaxation depend on three other things. Inherent energy of the tissue, how closely packed molecules are, and Barmar frequency matching. And these are the graphs you're going to start to see. Okay? So our T1 recovery graph looks like this. Where our signal is recovering from 0 back up to 100. And you can see here, when we're recovering, we're talking about how that vector recovers back up on that longitudinal axis. And this is the time it takes. So that's how it gets its name, recovery. It's going from 0 to 100, or recovering. And then you see your T2 decay curve, it's going down. And what it's talking about is how that vector is decaying or decreasing along that transverse plane. So once we flip it into that transverse plane and we turn off that RF pulse, it goes from 100% ultimately down to 0 once those tissues have fully decayed. And you can see here the x-axis for both is time. But take note at how the y-axis is labeled for each of these. T1 recovery, the y-axis is the longitudinal plane, or longitudinal magnetization. And then the T2 decay, the y-axis is the transverse magnetization plane. And why do you think it says coherent? Because remember, one of the steps, one of the reasons of resonance, right, was to put them in phase. But once we turn off that RF pulse, they're not going to resonate anymore, and they start to process out of phase. And then they decay rapidly. And you could put in here, next to time, milliseconds. Because it's going to happen very, very fast. Milliseconds. We'll get to the 63 and 37% here in a little bit. All right, and the third way MR images obtain contrast is through proton density, also referred to as spin density. So another name for proton density is spin density. And the definition of proton density is just the number of mobile hydrogen spins, or protons, per unit of volume. And we're not thinking about two-dimensionally anymore, like in X-ray, where we're dealing with a pixel. Our unit of volume is now three-dimensionally described, so it's going to be the voxel. So number of hydrogen spins, or protons, per unit voxel of that tissue. And ultimately, if we have a higher proton density, we're going to get more signal from that tissue. So in this image here, we have two voxels, one with what we considered low proton density because it doesn't have as many hydrogen spins within this voxel, compared to an area of high proton density where we have a lot more hydrogen protons. And you can see here how it's at different parts of the brain, and then what it looks like on our image. And when we have a higher area of proton density within the voxel, we're going to get more signal, which is brighter on our image. All right. So let's describe or go over these three things that T1 and T2 relaxation depend on. So we're going to go through these three things. All right, the first one, inherent energy of tissue. And what we're talking about here is the surrounding environment. So surrounding environment. So you're going to see this term lattice. So when we have low inherent energy, that means the molecular lattice, or the surrounding environment, is able to absorb energy from our hydrogen spins. So think of like the lattice as a sponge. It can absorb that energy a lot easier. So then the energy of our hydrogen spin goes down very quickly, so that's why it's referred to as low. If we have high inherent energy of the tissue, the surrounding environment, or lattice, cannot easily absorb energy from our hydrogen spins. So think of those surrounding tissues as like a kitchen paper towel, like one of those cheap brands, right? Not our, what are some of the brands out there? Braun, isn't it? The guy with the plaid shirt? I'm trying to think of it now. I just drew a blank all of a sudden. So not as easily absorbed from our hydrogen spin. So then the hydrogen spin retains more energy, so it has high inherent energy. So when we start talking about lattice, remember that is kind of related to T1 relaxation, because remember we had another name for T1 recovery, which was spin lattice. So this is especially in T1 relaxation or recovery processes, which rely on energy exchange with the lattice. And that's where we get that spin-lattice relationship. All right, the next one, molecular packing. So think of two different types of molecules. So think of, we have a beaker here, and we just remove fat from a person and then just dropped it into a beaker. It's just going to be this globule, right? It's going to be very closely packed. And so the neighboring spins are going to be very close to each other. Okay? Neighboring spins. Spin, spin. Compared to if we had water and we put water in a beaker, those water molecules are free-flowing and they're not going to interact with their neighbor as often as a fat molecule will. So think of water in a beaker, and these are all the water molecules. You can see its neighboring spin is not as close. So which one do you think is not going to give off energy to its neighboring spin as easily? Water or fat? Water. Okay. And we don't have just pure water in our body. So think of, when we talk about water, think of urine in the bladder, CSF within the ventricles or in the spinal canal. Those are our tissues that are most like water. But that's really the tissue that we're referring to. So this is especially important in T2 relaxation, are also called decay, which rely on efficient interactions, spin-spin, between magnetic fields of its neighboring hydrogen nuclei. And the third thing that affects T1 and T2 relaxation is Barmar frequency matching. This is when we're talking about matching between the molecular tumbling rate and the Barmar frequency of hydrogen. So different tissues tumble, and think of tumbling just like you were tumbling down a hill. kind of end over end. So when these molecules tumble at the same rate of our Barmar frequency, once again, we get an energy exchange that is more efficient. Remember, when we talked about efficiency of the energy being exchanged, we talked about resonance as well. But some tissues tumble at a different rate than our Barmar frequency, and you're not going to get as an efficient energy exchange. So which tissue do you think tumbles faster than the other? You had to think, water and fat. Say water?
Yeah.
You're right. Remember, it's free-flowing. And then here's a reminder about our Barmar equation. So perceptional frequency is equal to the gyromagnetic ratio, which is a constant, times our static magnetic field. So we have two extremes of contrast in MRI, and those are fat and water. And look here, this is a T1 weighted axial of the brain. And on this image, fat, which is right above our skull, on the periphery of our skull here, is bright in signal. And water, or CSF, remember, which is in our ventricles, our lateral ventricles here, is dark. And we'll get to why that is on a T1 weighted in a little bit. But just notice how our two extremes have a different shade or intensity in our T1 weighted image. And then just look at how what the molecule looks like. Here we have a saturated fat or unsaturated fat, very large molecule, and then water, just H2O, right? It's polarized, where one side is more positive than the other, and it just has 3 atoms. All right, let's talk about molecular binding for a second. So molecular binding is the way an atom shares its outer shell electrons, and that will have a direct effect on its atom's magnetic susceptibility. So the molecular binding of fat and water is very different. Let's talk about fat first. So those hydrogen protons, and look at them, there's a lot of them. They can be attached to carbon, they can be attached to oxygen, but there's a lot of them. But let's talk about those electrons surrounding that hydrogen. So in fat, hydrogen is bound to carbon, and they're very large molecules called lipids. So just the way that it's structured, the hydrogen proton keeps its outer shell electron. Okay? It's not going to give that outer shell electron to carbon. It's going to keep it. So it's going to orbit hydrogen. But let's talk about water. So we have 2 hydrogen arranged with one oxygen atom with water, H2O. In this case, oxygen tends to steal those electrons away from that hydrogen nucleus, because how many outer electrons are in oxygen? How many electrons are orbiting oxygen? 6, right? And remember, for that second shell, for it to kind of be complete, you want 2 more, right? You want 8. So it tends to steal that to become neutral, right? To have that outer shell complete, which makes the atom or molecule happier. Okay? And when that happens, this makes the magnetic susceptibility of the hydrogen in water higher than the magnetic susceptibility of hydrogen in fat. Because what's going on is it polarizes that molecule. So if oxygen is pulling 2 electrons towards it, it's going to be more negative towards the oxygen atom. And then towards the hydrogen up here, it's going to be more positive because you just lost 2 electrons. And any time where you have this dipole effect, it creates a stronger magnet, right? So that's how it affects magnetic susceptibility. So water has a higher magnetic susceptibility than fat. And when you plug that into our Barmar equation, so it's going to process actually a little bit faster than fat. So it has a higher Barmar or processional frequency than fat, just due to it being more magnetically susceptible. And it's just slight. Because this RF pulse that we're applying, that we described in terms of resonance, where it has to match, it's going to be a range of frequencies. It's not going to be exactly 42.57 on the dot. It's going to be a range. 42.13 all the way up to 42.97. So we get all those tissues which have slightly different processional frequencies. So then the hydrogen nuclei in water will process faster than the hydrogen nuclei in fat. This means that the nuclei in water will absorb more RF energy than the nuclei in fat. This results in a faster recovery in fat and a faster decay of fat tissue because it has absorbed less energy overall. And therefore, fat and water appear differently on MR images. So hydrogen in fat has a quicker T1 recovery time than hydrogen in water. We'll figure out what those values are by the end of this unit. But we know it's in milliseconds. And hydrogen in fat will also have a quicker T2 decay time than hydrogen in water. Okay. So with that being said, here is that T1 recovery and T2 decay curve, but we're going to start off with our T1 recovery curve. And remember, we said fat recovers a lot quicker than water. Okay? So we're starting to get contrast between the two tissues on our T1 recovery graph. And remember, T1 recovery is talking about when the nuclei are giving up energy to their environment, spin lattice. The lattice is the environment. And T1 recovery in the tissue is considered fully recovered when the longitudinal magnetization is 63% of its original intensity. So remember on that first graph, that had 63% for the T1 and 37% for the T2. That's where those numbers come into play. A tissue, and all tissues are considered fully recovered at 63%. It's kind of an arbitrary number, but we don't ever really want these tissues to fully recover, because then at that point, all the tissues will have the same intensity again, right? They'll all be at 100 again. So we can really highlight the difference in contrast between these tissues at 63%. That's where that number kind of comes into play. Remember, T1 recovery is unique to each tissue, but remember, fat recovers quicker than water because it gives off energy to its surrounding environment a lot quicker. Because remember, it's a very closely packed molecule. The surrounding environment easily absorbs that energy from that hydrogen spins. It's processing at a slightly lower rate, so it doesn't have as much energy to start compared to water. So those are all the reasons why fat recovers quicker than water. So we can define T1. T1 is a characteristic of tissue and is defined as the time it takes the longitudinal magnetization. We want to label this graph, just put M sub Z, to grow back to 63% of its final value. Right? So you're going to start to see this drawn in several different ways. So this is what an RF pulse looks like on a pulse sequence diagram. This is just the vector and the size of the vector as it regrows. And this is what we've talked about thus far, where we have the longitudinal axis over time. But at this point, what it's talking about is, okay, we applied that RF pulse to flip it into the transverse plane. So when that RF pulse is applied, the longitudinal magnetization goes down to 0, right? Because now it's in the transverse plane. But the moment this RF pulse turns off, and that's why it's drawn right at the same point where it's turned off, those tissues start to relax back up the longitudinal plane. Okay? Apply RF pulse, turn it off, tissues relax back up. And this is what the vector looks like as it regrows. But our tissues can't go past 100%. That's why it plateaus off. Okay? It can never be a larger value than you originally started with, right? It will always plateau off at 100%. All right? So when we're talking about T1 recovery, let's kind of summarize the differences between fat and water. So fat has a low inherent energy because it's giving off energy to the lattice very easily. So the lattice is easily absorbing energy away from our hydrogen spins and fat. It has a slow molecular tumbling rate. So the recovery is also going to be rapid because the tumbling rate actually matches the Barmar frequency a little bit better than the tumbling rate for water. So when it matches, we get better resonance and a more efficient energy exchange. Now compare that to water. Water has a high inherent energy because it's not easily giving off energy to its lattice or surrounding environment. Has a very fast molecular tumbling rate or mobility, so it recovers slowly. And that tumbling rate does not match the Barmar frequency as well, so it's a less efficient energy exchange. So this is all associated with T1 recovery and spin lattice. We haven't even discussed the neighboring spins yet, right? Spin, spin. We'll get to that with T2. So here is a graph, a T1 recovery graph, with all different types of tissue. So we have fat, white matter of the brain, gray matter of the brain, and CSF, which is water. And so you can actually chart how fast it reaches that 63% threshold. And here is the time in milliseconds. And it's all based on our static magnetic field, because it's all associated with our static magnetic field, because that's incorporated into our Barmar frequency, our Barmar equation. So when we're talking about 1 Tesla magnets, it only takes 200 milliseconds for fat to fully recover, hit that 63% threshold. Okay? 200 milliseconds at 1 Tesla. Very fast. But on the other hand, water takes a lot longer to recover, up to 63%. And you can see that with that black line right here. So at 1 Tesla, because remember, everything, all these tissues are field strength dependent, it takes between 2,000 and 2,500 milliseconds for it to hit that 63% threshold. So it realigns with B sub 0 slowly compared to fat. All right. So we've talked about T1. Now let's switch gears and talk about T2 decay. Yeah, go on. It's not non-existent because these two things are happening at the same time, but they're two separate processes. So it's good that you associate T1 with the surrounding environment. And that could be, other elements, just not the neighboring hydrogen nuclei, okay? It's giving off energy to the surrounding environment. But T2, and we'll talk about it here in a second, is strictly spin-spin. And that's the neighboring hydrogen nuclei. Yeah. So they are happening at the same time, but they are two separate processes. All right, T2 decay. So this is when T2 decay occurs when the nuclei exchange energy. And what we're talking about is our neighboring spins. That's where we get spin-spin relaxation. T2 decay is the time it takes for 63% of our transverse magnetization to be lost. So that's why you get that number that's 37 on this axis here. Because we start off with 100%, it has dropped to 37, and the difference between 137 is the 63. So that makes sense compared to our other graph, right? Tissue was considered fully recovered at 63. Here, we're talking about a tissue is considered fully decayed when it's lost 63% of its transverse magnetization, or you could say has 37% left. Okay, there's a couple ways you can phrase it, and the registry commonly tries to confuse you with that. It's lost 63%, or it still has 37% left in terms of a transverse magnetization. And we know T2 decay, just like T1 recovery, is unique to each tissue. We can define T2 as well. So T2 is a characteristic of tissue and is defined as the time that it takes for transverse magnetization to decrease to 37% of its starting value. So see how it's described this way versus this line right here, 63 versus 37. So just see how it's phrased, because that will be a common thing you'll have to decipher. So T2 decay depends on spin-spin interactions. And with fat, we have molecules that are packed closer together. So when they're closer together, remember, if you have neighboring spins that are closer together, those are two little magnetic moments. And they're going to interact with each other, and they're going to cause each other to dephase a lot faster. Remember, dephase, that's incoherent. They're out of line in that precessional path. So they're going to dephase a lot quicker. So imagine all those little vectors are in phase. That's what's showing here. But then as they interact with its neighbor, they dephase, meaning they start to fan out. You'll see these images in the book, and this is what they mean. All these little vectors are fanning out and dephasing. And what's happening is you had good signal when they are in phase with each other, but as they start to fan out, it rapidly declines. And what is this right here, this little image? Free induction decay. So remember that from last unit. So this is your free induction decay. And that's where we get that drawing and that graph. It's really just charting the signal as it goes down. Okay. But water, on the other hand, the molecules are spaced apart more because they're free flowing. They're not going to interact as likely, so the chance that they're going to interact with their neighboring spin is not as likely. So as a result, the spins, they do dephase, but they're not going to dephase as rapidly. So if you think about this fan, it's not going to fan out as quickly. Okay? So that's why here it's showing it's fanned out completely versus here it's only fanned out a little bit. When it fans out more, the signal drops quicker. Okay? So let's talk about our two tissues, fat and water. So first, fat. T2 decay in fat. That's when we have loss of transverse magnetization is rapid, because we know that fat molecules are very closely packed together. Our neighboring spins give off energy to our neighboring spins. So our T2 decay time of fat is short. And at a 1 Tesla magnet, it's even quicker than its recovery time, 100 milliseconds. So as we can see, fat with this yellow slope line hits that 37% threshold at 100 milliseconds, very quickly. As opposed to water, it's not going to interact with its neighboring spins as likely, so it takes longer to get to that 37% threshold, and the time is about 2,500 milliseconds. So about the same time as its recovery. But you can see how we're starting to get the contrast between these two tissues, not only on a T1 chart, but on a T2 decay chart. So here's just kind of a summary slide. So the longitudinal magnetization recovers quicker in fat than water, and the transverse magnetization decays quicker in fat than in water. And here are the times. And once again, it's all field strength dependent. So all these numbers are going to be different based on our field strength. But for this test, all you'll have to know are the numbers at 1 Tesla. Okay. So then going back to our original drawing with our longitudinal axis, and our transverse axis. So I have to kind of show you one step that happens before we get to this, okay? So when we start out with fat and water have the same length and vector size, okay? They both flip into the transverse plane. And at this point, even though I'm showing this one a little bit bigger, just imagine that they're the same size so you can see the two. And at this point, they have 100% signal intensity, but there's no contrast between these tissues. So we don't really take the signal at this point. We don't receive the signal at this point because it would be pointless. So we turn off that RF pulse that's coming, B1. And remember, fat decays quicker on that transverse plane. Since it decays quicker, it recovers faster on the longitudinal plane. You guys see that? Okay. Water decays slower on the transverse plane, but then it also recovered a lot slower on the longitudinal axis. Okay, so we're starting to look like that. Okay, you see that? So we don't wait for water to fully recover up the longitudinal axis before we hit it with the second RF pulse. You see that? So we have another RF pulse coming, and we have two different size vectors at this point, which is good because we're starting to create contrast between the tissues. And when we apply that second RF pulse, the fat vector is going to be bigger than the water vector. You see that? And now we have contrast. And we have the vectors in the transverse plane, which is ultimately where we receive the signal. Okay? So for a T1 weighted image, to get T1 contrast, we manipulate the parameters to get this desired effect. Okay, and we'll talk about that here in a little bit. But at this point, what you know is that fat has a higher signal on a T1 weighted image than water because of the size of the vector in the transverse plane. Okay? So with that being said, this is what an image looks like. Okay? So fat realigning with the longitudinal axis creates a larger vector for when that second RF pulse hits. Because even though we have a larger vector here in the longitudinal axis, remember, we can't ever receive signal unless it's flipped into the transverse plane. And water recovers slowly, so then it's going to have a smaller vector, and then when it gets flipped down in the transverse plane, it will ultimately have less signal. So then let's point to our two structures. So then fat is right here on the very edge, subcutaneous fat, and then water right here on our image, CSF. So we're starting to get contrast. And the next time we meet, we're going to start talking about how we manipulate things like TR and TE to get this desired contrast. And once we start manipulating those things, that's where we call it weighting, because we're weighting it more heavily for a T1 image versus a T2. Okay? So we're going to stop there. Any questions?